Welcome to this Forge College Explainer. All right, go ahead and put on your yellow tape and grab your magnifying glass, because today you're a blockchain forensic investigator arriving at a smart contract crime scene. Now, in our last lesson, Arrays and Access Patterns, we learned how to successfully navigate around data structures. But what happens when things go terribly, horribly wrong? Well, today we're going to figure out exactly how to stop your contracts from spontaneously combusting in production.
Here's a quick look at our agenda for the investigation. We'll start with the buggy crime scene, then look at out-of-bounds indexing bugs, unsafe array resizing, storage aliasing pitfalls, the debugging toolkit, and finally, a quick summary and next steps.
Section 1. The buggy contract crime scene. Let's do an autopsy of buggy storage.
So we're kicking off our investigation with a deliberately flawed contract that's just constantly crashing. It's honestly an absolute mess of broken logic, and we need to figure out why. Here's our core evidence. This contract has three specific functions, acting as our primary suspects for breaking the code in production: get item, remove last, and duplicate first two. I mean, each of these looks innocent enough on the surface, right? Just standard array operations. But underneath, they are hiding some incredibly sinister assumptions that will absolutely wreck your deployment.
Moving to Section 2. Out-of-bounds indexing bugs. This is our first suspect.
This one usually pops up when we get a little too overconfident about what data actually exists in our contract. By definition, an out-of-bounds access happens when you try to pull data from an index that just isn't there. If your getItem function lacks an explicit bounds check, asking for an index that doesn't exist will cause the whole transaction to revert. At the EVM level, this triggers a state rollback to protect against memory corruption. In simpler terms, it's kind of like trying to open locker number 100 in a hallway that only has 50 lockers. The contract just panics and shuts the entire operation down. But here's the easy fix. Adding an explicit length check guards your assumptions and completely neutralizes the vulnerability. Look at the left side. Our unsafe code is basically just blindly hoping the index is there. But on the right, that tiny require statement forces the contract to actually verify the index exists within the bounds before proceeding. It is literally one small line of code that prevents a massive headache.
All right, Section 3, unsafe array resizing. Suspect number 2.
Now, you might think shrinking an array is foolproof, but if you don't look before you leap, you are in for a nasty surprise. An unsafe pop happens when you try to remove an item without checking if the array is already empty. Calling a pop operation on an empty array will silently revert in recent Solidity versions. But in older versions, oh man, it causes an underflow. This wraps the array length to the maximum possible integer, leading to this unpredictable, unmitigated chaos where an attacker can suddenly access any storage slot in your contract. You're essentially asking the EVM to delete something from nothing.
So the absolutely crucial point here is to always ensure your array actually has elements to pop before executing the removal. The fixed code on the right explicitly requires the length to be greater than 0. It verifies there's actually a piece of data to remove, keeping your logic totally safe and preventing that terrifying integer underflow.
Next up, Section 4, storage aliasing pitfalls. Suspect number 3.
Now we arrive at the most subtle and honestly most dangerous suspect of them all: unintended storage references. This is the exact kind of bug that will make you tear your hair out during debugging. Our duplicate first two function accidentally creates a shared reference. That means if you update the first item later, it unexpectedly mutates the duplicated item too. They become magically and disastrously linked together because both variables are resolving to the exact same 32-byte slot address in the contract storage.
To wrap your head around this, think of storage as a persistent, bolted-down safe. It's expensive and it's permanent. Memory, on the other hand, is just an ephemeral snapshot. It's like a temporary sketchpad. When you accidentally point your temporary logic directly at the safe's combination lock instead of just writing it down on your sketchpad, well, modifying things locally ends up modifying the safe permanently. To fix this mess, we create a temporary struct in memory. This guarantees we're copying isolated values rather than creating a dangerous storage pointer. On the left side, using the storage keyword created that dangerous pointer. But on the right, by using the memory keyword and building a completely fresh copy of the struct, we break that link completely and safely assign isolated data.
On to Section 5, the debugging toolkit. Time to catch these bugs red-handed.
Now that we know who our suspects are, we can't just fix them once and hope they never return. We need to set up a forensic workflow to reliably catch them using frameworks like Hardhat and Chai. Here is your standard operating procedure: reproduce, isolate, assert, fix, and validate. This specific cycle is a vital habit you've got to build before deploying any complex data structures. Seriously, you have to actively try to break your own code just to prove that it works. Here is how this workflow actually builds a targeted test suite. You have to intentionally cause reverts and use Chai to expect those specific transaction failures to test for out-of-bounds errors. You must test empty arrays to catch unsafe pops. And you definitely need to attempt mutations on one slot to assert that the others remain unchanged. That's how you expose those tricky storage aliases. Your tests basically need to be as ruthless as a real-world attacker.
Finally, Section 6, Summary and Next Steps. Case closed. Okay, so we've successfully autopsied our buggy contract, identified the root causes of its spectacular failures, and mapped out a workflow to prevent them from striking again. The main thing you should take away from all this is that relying on assumed default states is super dangerous. But disciplined testing, that keeps your contract logic structurally sound. Always guard your indexes, safely resize your arrays, isolate your memory, and stick to that debug cycle. Up next in the Solidity from Zero track, we'll be preparing for mappings. This has been a Forge College explainer, and we'd absolutely love for you to visit forge.college to learn more about mapping fundamentals and other really exciting Web3 topics. But before we go, I want to leave you with a quick question to chew on. We know how to handle missing items in an array now, but how will these exact same edge cases apply when keys don't exist at all in a mapping? I'll let you think about that one. Thanks for investigating with us today, and we'll see you in the next one.